There is a machine out there, a small car-sized artifact of 1970s engineering, currently more than 25 billion kilometers from Earth. It has been traveling for nearly 5 decades, carrying a golden record in the hopes of a species that was still figuring out how to put a man on the moon when it launched. It flew past Jupiter and Saturn, sending back images that rewrote textbooks. It crossed the boundary of our solar system, becoming the first human-made object to taste interstellar space. It is still running. It is still talking. But what it has been saying lately is forcing scientists to rethink everything they thought they knew about what lies beyond the edge of our sun's influence. Voyager 1 launched on September 5th, 1977, just a few weeks after its twin, Voyager 2. The original mission was simple by today's standards: visit Jupiter and Saturn, take pictures, collect data, and send it all back home. It was a grand tour of the outer planets, a once-in-a-lifetime alignment that occurs only once in 176 years that allowed a single spacecraft to visit multiple giants. The mission was considered a resounding success. Voyager 1 captured stunning images of Jupiter's Great Red Spot, discovered active volcanoes on its moon Io, and revealed the intricate complexity of Saturn's rings in a way that left scientists stunned. After the planetary flybys, it kept going. It was given a new mission, to be humanity's ambassador to interstellar space. In August 2012, Voyager 1 crossed the heliopause, the boundary where the sun's influence ends and the interstellar medium begins. It was the first probe to sample this region directly, detecting a sudden change in the surrounding medium that matched theoretical expectations. It was a historic moment, a tangible sign that something built on Earth had left the neighborhood. Today, it is more than 160 astronomical units from the sun, receding at several astronomical units per year. At its current speed of roughly 38,000 miles per hour, it would take about 40,000 years for Voyager 1 to come within 1.6 light years of another star. It is, for all intents and purposes, a permanent part of the galaxy now. The sheer scale of the distance is almost impossible to grasp. A radio signal travels at the speed of light. It takes approximately 22.5 hours for a command from Earth to reach Voyager 1. Why 1? That means if an engineer at NASA's Jet Propulsion Laboratory sends a command at 8 a.m. on a Monday, they will not receive a response until Wednesday morning. It is a 2-day turnaround for a single question. This is the raw physics of interstellar distance. It is also the core challenge of troubleshooting a glitch on a machine you cannot see, touch, or repair. The mystery signal that has gripped headlines is, in reality, a family of anomalies that have been cropping up for years. In late 2023 and early 2024, Voyager 1 began sending back data that was, in the words of NASA, a garbled and ghostly stream of binary code. It was receiving commands, and its instruments were collecting data, but when that data was packaged and sent back to Earth, it was a jumble of 1s and 0s that made no sense. It was like watching a trusted old friend start to say things that didn't quite line up with reality while they still insisted they were fine. The root of this particular problem was eventually traced to the flight data subsystem, a vital component that acts as the probe's packager. The FDS takes all the scientific and engineering data, organizes it, and prepares it for transmission. The team suspected a single broken memory chip within the FDS had failed, corrupting the outgoing data stream. By April 18, 2024, engineering data transmission was restored. But the mystery has not entirely gone away. Even before the FDS glitch, and in some respects still unresolved, Voyager 1 was sending back strange data from its attitude and articulation control system. The AACS is responsible for keeping the spacecraft's high-gain antenna pointed precisely at Earth. Without it, Voyager 1 would be a silent, drifting monument. The system appears to be functioning perfectly. The spacecraft's antennas is aligned and the signal strength is not weakening. The problem is the telemetry data the AACS is sending back about its own status. It is reporting invalid information, readings that appear to be randomly generated or physically impossible. The data from the AACS doesn't reflect what's actually happening on board. The spacecraft is operating normally, but it is sending back readings that say otherwise. The problem has not tripped any onboard fault protection systems, which means the spacecraft itself doesn't think there's a problem. It's a contradiction, a digital hallucination that emerges from somewhere deep in the 45-year-old circuitry. Suzanne Dodd, the project manager for the Voyager missions, described the situation perfectly. A mystery like this is sort of par for the course at this stage of the Voyager mission. We're also in interstellar space, a high radiation environment that no spacecraft have flown in before, so there are some big challenges for the engineering team. The Voyager probes are running on borrowed time. Their power source, a set of radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity, loses about 4 watts of power every year. Engineers have been carefully turning off non-essential systems to keep the critical science instruments alive. In February 2025, the cosmic ray subsystem was shut down. On February 27, 2026, during a routine roll maneuver, the power dropped sharply, forcing an earlier than planned shutdown. The low-energy charged particles experiment, which had been operating almost without interruption since 1977, was shut down on April 17, 2026. Voyager 1 now has two operating science instruments, the magnetometer and the plasma wave subsystem. Kareem Badarudin, the project manager, stated that while shutting down a science instrument is not anybody's preference, it is the best option available. The thrusters have also been a persistent challenge. The backup thrusters began clogging in 2025. In a remarkable engineering achievement, the team successfully revived the primary thrusters on March 20, 2025. Todd Barber, a propulsion engineer, called it yet another miracle save for Voyager. The revival process involved carefully heating the thrusters, fuel lines, and valves to clear blockages, a delicate operation that took months to plan and execute. It was a testament to the ingenuity and persistence of the Voyager team, who have been solving problems on this spacecraft for longer than many of them have been alive. And Sean Kazarian, the NASA engineer responsible for communicating with the Voyager probes, is younger than the spacecraft he talks to. At 25, Kazarian is among a new generation of engineers at NASA's Jet Propulsion Laboratory working to keep the geriatric but resilient spacecraft going. Every time I talk about Voyager, I kind of treat it like my parents, he said. As a human gets older, they have all these problems. A spacecraft is similar. The older it gets, the more problems. Working with the aging spacecraft requires ingenuity, doggedness, and Zen-like patience. Each time Kazarian sends a command to one of the Voyagers, he has to wait a couple of days for a response. But beyond the technical glitches and the power struggles, Voyager 1 has made a discovery that is genuinely rewriting the textbooks. Since crossing the heliopause, the spacecraft has detected an unexpected zone of extremely hot particles just beyond the edge of our solar system. Scientists have aptly named this region the Wall of Fire because it is a massive zone of energetic particles that creates an intense heat wave at the solar system's edge. Temperatures in this region soar to nearly 54,000 degrees Fahrenheit. It seems like something out of science fiction, but these scorching temperatures are very real and hidden away in the depths of space. Voyager's instruments have detected a surprising rise in both temperatures and the density of particles as it crossed the boundary of the solar system. For many years, researchers theorized that this edge could be cold and scattered, but Voyager's first findings have turned that notion on its head. The recent findings also show that magnetic fields inside the heliopause and subsequently in interstellar space are surprisingly similar. Scientists expected dramatically distinct magnetic environments between our solar bubble and the vast galaxy after the heliopause, but the data shows a more continuous transition than anyone predicted. The discovery of this wall of fire is not just a curiosity. It has profound implications for our understanding of how our solar system interacts with the galaxy. The heliopause is the outermost boundary where the sun's magnetic influence and solar wind pressure meet the cold and desolation of interstellar space. This region acts as a shield, protecting the solar system from the most energetic cosmic rays coming from deep space. The wall of fire is a dynamic, active boundary, not a passive barrier, and it is constantly changing in response to solar activity. As Voyager 1 probes this frontier, it helps scientists answer questions on how our solar system interacts with the rest of our galaxy and how far the sun's influence really extends. Each faint signal Voyager 1 sends back to Earth has to travel more than 24 billion kilometers to reach us, and each of those signals is just a fragment of the answer. But now we know that our solar system doesn't simply fade into the galactic vastness. It ends in a place of turbulence and extreme energy, a boundary zone where forces from within and beyond clash and shape each other in unpredictable ways. One of the most significant findings from Voyager 1 concerns the nature of the magnetic field in the very local interstellar medium. The spacecraft has observed a prolonged period of elevated magnetic field strength, a phenomenon known as the magnetic hump. This hump began around 2020 and persisted until roughly 2022. It represents a fundamental reorganization of the interstellar environment, a large-scale structure that scientists are still struggling to explain. Some researchers believe it is the result of a massive solar transient, a global merged interaction region, that propagated all the way from the sun to the edge of the heliosphere, and then pushed into interstellar space. The plasma density in this region is about 0.147 atoms per cubic centimeter, which is very close to the density that would produce the highest frequency heliospheric radio emissions observed by the Voyagers in the 1980s and 1990s. This suggests that Voyager 1 has reached a region of the interstellar medium that is representative of the source of those ancient radio signals, connecting the spacecraft's current observations with data collected decades ago. The Voyager probes have become our first interstellar weather stations. They are sampling a region of space that no spacecraft will likely visit again for decades, perhaps centuries. The data they send back is teaching us about the composition of interstellar gas, the behavior of magnetic fields, and the nature of cosmic rays. For instance, the density of the interstellar gas beyond the heliopause is significantly higher than the solar wind in the outer heliosphere. This is because the interstellar gas is much colder than the solar wind, and pressure equilibrium demands a higher density. The composition is estimated to be about 0.2 hydrogen atoms and 0.06 protons per cubic centimeter, compared to just 0.002 protons per cubic centimeter for the solar wind. This stark difference in density and composition between the two regions highlights the dramatic change in the environment as one crosses from the heliosphere into interstellar space. The cosmic ray data from Voyager 1 is equally revealing. Since crossing the heliopause, the spacecraft has observed a significant increase in cosmic ray flux, particularly in the energy range of 1 to 10 MeV. This increase is accompanied by a dramatic decrease in the flux of anomalous cosmic rays and a steepening of the cosmic ray energy spectrum. These changes are consistent with the spacecraft entering a region where the solar wind no longer shields the solar system from the full force of galactic cosmic rays. This data is crucial for understanding how the heliosphere modulates the flux of cosmic rays reaching Earth and other planets, which has implications for space weather and even climate studies. The heliosphere acts as a shield, deflecting about 75% of galactic cosmic rays, and Voyager 1's data is helping scientists understand the physics of this shielding effect. The magnetometer data from Voyager 1 has also revealed that the interstellar magnetic field is draped and compressed as it piles up against the heliosphere. This compression creates a region of enhanced magnetic pressure that contributes to the wall of fire and plays a role in shaping the boundary of the solar system. The magnetic field direction, strength, and turbulence in the interstellar medium are now being measured directly for the first time, providing critical constraints on models of the local interstellar cloud and the galactic magnetic field. When we hear that Voyager 1 has sent back a signal that scientists can't explain, it is not a reason to panic. It is a reason to marvel. The signal is a reminder that we have built something that has outlasted its creators. It is a reminder that our reach into the cosmos is fragile and finite. It is a reminder that the universe is vast and indifferent, and that our machines, no matter how well built, will eventually fall silent. The final messages from Voyager 1 are not just data. They are an elegy to what is possible when we reach beyond our world. They are a testament to human curiosity, perseverance, and the stubborn refusal to accept that there is nothing left to discover. The window is open now, and Voyager 1 is floating through it, whispering its faint signal across the void. Long after it falls silent, that signal will continue to travel, carrying a faint echo of Earth into the spaces between the stars. And that, perhaps, is the most powerful message of all.